Greetings, everybody. Learning is a hobby here. I want to go over my summary for Chapter 2 in Watkins' book Topics in Commutative Ring Theory. There seems to be something going on with my internet. I don't know if it has to do with the heat or something, but it keeps cutting in and out. This is like the third time I've tried to record this video, so I'm getting a little bit frustrated, but just bear with me. Let me start on my notes again here and see if we can get through this video without the internet cutting out. Um, okay, so again, just like I said in my last video, my summary is just a bunch of bullet points about the most important aspects of the chapter. You should read the chapter yourself in Watkins' book because he has a lot of more background material that he talks about in each of the chapters than will appear just in my summaries. So you should read through the chapters because you'll be missing a lot if you don't do that. But let's get to my summary here. We'll get to the important stuff in chapter 2. We start with a definition. In the last chapter, we ended with the definition of a subring, but the really important substructures of a ring are the ideals, not necessarily the subrings. So here's our definition of an ideal. So an ideal of a ring R is a subset I of R that is itself a group under addition and is such that if R is an element of R and A and I, then RA equals I. Sorry, it's an element of I. All right. If you don't know what a group is, Watkins does give the axioms here. And just to mention it, axiom 1 actually follows from axiom 2 and 3, so you don't really have to state it. But axiom 1 does guarantee here that you have a non-empty set, and in order for something to be a group, it has to be non-empty. So I don't know, you could start by saying it has to be non-empty. Anyway, the additive identity has to be an element of I in order for it to be a group. Uh, I is closed under has to be closed under addition, and if A is an I, then the multiplicative inverse has to be an element of I, and for addition in I is associative. And if those four things are satisfied, then you're guaranteed that the subset is a group. Right? In addition to being a group, I must quote unquote absorb multiplication from R. So that's the second condition here. So if R is an R and A is an I, then RA is an element of I. Okay, just a note, an ideal is almost a subgroup, except it need not contain the multiplicative identity 1, and a subring is almost an ideal, except it need not satisfy the strong condition of absorbing multiplication from R. Right, and now there's a nice way of showing that a subset of a ring is an ideal. There's two conditions only that you really have to look at, which I have listed here. So condition 1, if A, B are elements of I, then A minus B is an I. And 2, the the ideal absorbs multiplication from the bigger ring. So if R is an R and A is an I, then RA is an I. So condition 1 guarantees that I is a group under addition, and then property 2 guarantees that that I absorbs multiplication from the bigger ring. All right, and now we have some examples. Example 1, the even integers, which we usually denote like this, 2z, is an ideal of z. We saw in the exercise set for chapter 1 that z was not a subring, but it is actually an ideal. Sorry, that 2z was not a subring, but that 2z was a. Now we know that 2z is actually an ideal of z. Right? Example 2. A lot of these examples involve propositions that need to be proved. So I wrote the propositions in a box here just to, you know, show that it's a proposition. The example involves a proposition rather than sort of like a calculational example. So here's the proposition in example 2. Whenever an ideal contains the identity element, it must be the entire ring. And here's my proof. Let I be a subset of R, be an ideal, and let the multiplicative identity be an element of I. Then for R and R times 1 equals R, which is an element of I because I absorbs multiplication from the bigger group, right? Therefore, R is a subset of I, and we already know that I is a subset of R, therefore I has to equal R. Right, definition next. Let R be a ring, the polynomial ring over R, denoted by this notation here, which I'll read R of X, but really you should, when you see the symbol, you should think it's the set of polynomials in a single variable where the coefficients come from the ring R. So it's a polynomial ring over R. Uh, and like I said, um, well, this is the definition. It's the ring of polynomials with coefficients from R. All right. If f is an element of that ring, then f of x is a polynomial, something that looks like this, where all the coefficients come from the ring R. And just some vocabulary here, which you're probably familiar with already, but here we're defining polynomials from an arbitrary with coefficients from an arbitrary ring, which is not necessarily something that you looked at. You didn't look at rings in like algebra or pre-calculus or anything like that. So A0 is called the constant term, and provided the AN is not zero, n is the degree of the polynomial. Right, example 3, let R be a ring and I a subset of the polynomial ring in X with coefficients from R, where each polynomial in I has zero constant term. Then if FG are elements of I, then f of x is a polynomial that looks like that. G of x is a polynomial that looks like that, where without loss of generality, we can assume that m is less than or equal to n. And then if you look at their difference, f minus g of x is when you simplify everything, you get a polynomial that looks like that one that I have written out here. And notice that f minus g has zero constant terms, so it's an element of I. And then also we have to show that it absorbs multiplication from the bigger ring. If h of x is a general polynomial in the ring R of x, and f of x is a polynomial from the ring from the ideal I, then f times g, notice, is when you multiply them out, notice that you get a polynomial with zero constant term. Therefore, it's an element of I. Therefore, I is an ideal of R of x, right? It's closed. The two properties, right, are satisfied. Right. Example 4. Let R be a ring and J be the set of all polynomials in R of x, having only even powers of x. Then notice that J is a subring, but not an ideal, since if f is an element of J, then g of x equals x times f of x has all odd powers of x, which implies that g is not an element of J. So J does not absorb multiplication from R of x. Similarly, note that I of x that I of x equal uh sorry, I think I just used this notation to denote the constant polynomial where the constant is one. So that's the multiplicative identity in the ring R of x, right? So if that is an element of notice that that is an element of J, but that J is not the entire ring. Right? That's just another way that you can see that J is not an ideal. Right, example 5, let R be a ring and let A and R, let I be the set of all multiples of A. Then here we're looking at an ideal that looks like this, and we can prove that it's an ideal. If X, Y are elements of I, then X equals RA, Y equals SA for some RS and R. Then if we look at their difference, notice that we get a multiple of A, which shows that it's an element of I. And then 2, let B be an element of R. Then for any RA and I, B times RA equals BR times A. Notice that's a multiple of A, which means it's an element of I. Therefore, I is an ideal of R. And actually, ideals of this form are called principal ideals, which we define next in definition 2.2. So let R be a ring, let A be an element of R, then the ideal I, which has the same definition that we had up above, is called called a principal ideal. We say that the ideal I is generated by A, and usually write the ideal as A in parentheses, or occasionally as RA or AR if we wish to emphasize that we're multiplying the element A by elements of a particular ring, and the order that you write the product in makes a difference if you're not in a commutative ring, but if you're in a commutative ring like we are in Watkins' book, then RA is the same ideal as AR. Sometimes they also use the notation with the pointy brackets around A, which is common in group theory also when you're looking at cyclic groups. But anyway, sometimes that notation is used, but Watkins uses the notation that we just described up above. All right, example 6, the ideal in example 3 is the principal ideal generated by X. So let's prove that. Let I be the ideal of polynomials in R of X with zero constant term. Take f and I, then f of X equals that polynomial there, which if you factor out an X is equal to X times that polynomial that has a not necessarily zero constant term, right? Which is X times G of X, where G of X is this polynomial here. Notice that's an element in R of X. So F is an element of the principal ideal generated by X, implies I is a subset of that principal ideal. Next, take F in the principal ideal generated by X, then F of X equals X times G of X. For some G of X, some general polynomial that looks like this, then F of X equals summation I going from 0 to n, AI, X to the I plus 1. And notice if you take out the zeroth term, you get a0 times x plus the remaining terms. And notice that there is no constant term. There is zero constant term. All right. Therefore, the principal ideal generated by x is a subset of I. Therefore, the principal ideal generated by x is equal to I. Right. So that example that we looked at in example 3 is actually a principal ideal. All right, some notes here. Richard Dedekind introduced the concept of an ideal and recognized conditions 1 and 2 as being of fundamental importance. And just a historical note, Dedekind was actually a student of Gauss. Ideals can be thought of as a generalization of the concept of number. In particular, we can identify a number with the set of other numbers that it divides, meaning, sorry, let me just readjust here, meaning the ideal generated by the number. Right, example 7, all ideals of the integers are principal. Here's my proof. Let I be an ideal of Z, then either I is the zero ideal, meaning it's the principal ideal generated by 0, which is, it only has that one element in it. It's just 0, right? Or else I contains some non-zero integer n. Either n or not negative n is positive by trichotomy. So assume without loss of generality that n is the positive one. Then I contains a smallest positive integer by well ordering. We can assume without loss of generality that n is this least positive element. Since n is an element of I, an is an element of I for any a in Z. Since I absorbs multiplication from Z, so the principal ideal generated by n is a subset of I. Next, take a in I, then a equals nq plus r for some qr in Z, where r is greater than or equal to 0, less than n. That's by the division algorithm. Then r equals a minus nq. So r is an element of I. Since a and negative nq are elements of I, and I is closed under addition. However, r greater than or equal to 0, less than n implies that r has to be 0 since n was the least positive element of I. So a is a multiple of n. So it's an element of the principal ideal, which means that I is a subset of the principal ideal generated by n. So the two ideals are actually the same ideal. All right, definition 2.3, let I be an ideal of a ring R. A coset of I is a set of the form A plus I, where it's the set of all A plus little I, where I is an element of I, where A is an R. The element A is called a representative of the coset A plus I. Right, and then here we have an example. The principal ideal generated by 5 is an ideal of Z, and it has 5 elements. The cosets, there are 5 of them. They're generated by, they're generated isn't really the right word, but the cosets you get by taking the ideal and you add, the possible remainders that you would get upon division by 5. So 0, 1, 2, 3, 4. So these are the cosets. Cosets are not necessarily an ideal. Like 0 plus the ideal 5 is generated by 5 is an ideal, but for example, 1 plus the ideal generated by 5 is not an ideal. It's a coset of the ideal. Right. Note that each of these cosets are disjoint from each other and that Z is the union of those cosets. Such a collection of subsets is called a partition. Right? And a given coset can be represented by any of its elements and only by these elements. Right. Next, we get to Basic properties of cosets. There's four of them here. Let I be an ideal of a ring R. Let A be elements of R. Then the cosets of I have the following basic properties. One, A plus I equals I if and only if A is an element of I. Two, A plus I equals B plus I if and only if A minus B is an element of I. Three, A plus I equals B plus I if and only if A minus B plus I is equal to I. And lastly, four, the two cosets A plus I and B plus I are either disjoint or equal. So let's prove all four of those down here. Right, number one, let A plus I equal I. Then A equals A plus zero, and zero obviously is an element of I, so that's an element of A plus I. But A plus I is equal to I, so that means that A is an element of I. Next, let A, so remember these are if and only if, so you have to do both directions. Next, let A be an element of I. Then for B in I, A plus B is an element of A plus I, and that implies B equals A plus B plus minus A, which is equal to, by associativity, A plus B minus A, which is an element of A plus I. So I is a subset of the coset A plus I. Also, if B is an element of A plus I, then B is A plus I for some I in I, which implies B minus A is equal to I, which is I is obviously an element of I, which implies that B minus A plus A equals B plus minus A plus A, which is B plus zero, which is B, which is an element of I. Therefore, A plus I is a subset of I. So A plus I equals I. All right. Property two, let A plus I equal B plus I. Then if A plus I is an element of A plus I, then A plus I is an element of B plus I because they're equal, right? Implies A plus I equals B plus J for some I, J, and I. Then A minus B is J minus I is an element of I. Next, let A, B be elements of R such that A minus B is an element of I. Again, you have to do both directions, right? It's if and only if. Take A plus I and elements of A plus I, then A plus I equals A minus B plus I plus B. I'm just adding zero in a convenient way here, which is B plus in parentheses A minus B plus I, right? So addition is associative, which is obviously an element of B plus I. So A plus I is a subset of B plus I. And a similar argument shows that B plus I is a subset of A plus I, but I skipped it because it's virtually identical. So that means that A plus I equals B plus I. All right, number three follows directly from the previous two propositions, so I'll skip that. And lastly, number four, assume A plus I intersect B plus I is not empty, so meaning they're not disjoint. Then there is some element C in A plus I intersect B plus I, which implies that C is A plus I, which is equal to B plus J for some I, J, and I. Then A minus B is J minus I, which is an element of I, obviously. And two implies that A plus I equals B plus I, and that proves all four of those properties. Okay, definition 2.4. Now we get to the operations that we can perform on cosets, which will give us the ring structure of a quotient ring in a second. Right? Let I be an ideal of a ring R, then the operation of addition on the set of cosets of I are given by this operation here. So if you take A plus I plus B plus I, we define that to be A plus B plus I. And then the operation of multiplication is defined in a natural way as well. A plus I times B plus I is equal to AB plus I for AB and R, right? Problem 223 in the exercise set for chapter 2 asks the reader to verify that these operations are well defined. So that's something that we need to verify for this in order for these operations to really make sense. But we'll do that in the exercise set, so I'm not going to do that here. Okay, then we get to the definition of a quotient ring finally. Definition 2.5, let I be an ideal of a ring R, then the quotient ring of R by I is the ring of cosets of I, where addition and multiplication of cosets are defined as above. We denote this ring by R mod I, and you read it R mod I. All right, problem 224 asks the reader to verify that R mod I is indeed a ring, so we'll do that in the exercise set. And the zero element of R mod I is 0 plus I, or in other words, it's the ideal itself. And the multiplicative identity is 1 plus I. Right. Example 8 revisited here, just so we can see an example of a quotient ring. Z mod, the principal ideal generated by 5 is the ring of integers modulo 5, or in number theory, we would usually write this as Z with a subscript of 5. So in other words, there's 5 elements here. It's all of you can kind of think of them as the equivalence class, not kind of, they are the equivalence classes uh, of the integers upon division by 5. So you get all the remainders, in other words. So 0 plus 5, 0 plus, I'll just call it I. So let I be the principal ideal generated by 5. Then you get 0 plus I, 1 plus I, 2 plus I, 3 plus I, 4 plus I. Okay. Think this is the last note here in the chapter. So the terminology quotient ring has nothing to do with quotients or fractions. Rather, the term and notation R mod I suggests that I factors or partitions or divides the ring R into cosets, each having the same size as I. Excuse me. Um, so it's sort of like the similar a similar construction as we did in linear algebra when when you construct um, quotient spaces by modding out by a subspace. Same thing in group theory. If you mod out the larger group by a normal subgroup, you get a quotient group. And in ring theory, if you quotient out by an ideal, you get a quotient ring. Okay, so that's chapter 2 in Watkins' book. I'm going to be doing the exercise set in a different video because, like I said, this chapter was a little bit longer than chapter 1. So I'll do those problems in a separate video. I'll see you guys in the next one. Let me know what you think down below, and keep learning, everyone.